Can you hear me? Can you hear me now? Okay. Although I stand to be corrected. I see. I think Shell is basically an interface for programs to be able to communicate with the kernel of the operating system. That's because the operating system itself we can't see, so we can't see the kernel. So we just need like an interface that will help us to send our commands or our calls down to the kernel and also get a feedback. So it basically uses the idea of the standard um, input stream and the standard output stream. That's all I can say.
Okay.
All right. Thank you very much for that response. Thank you very much. Another device is named Steven from here. Do you have something else to say?
Yeah. Let me just say something. Let me say a shell is a mediator between the kernel and the user. It supplies an interface to us, which is a prompt
Okay.
for us to be able to pass a command. Then it picks up that command and then relate it to the operating system. So we communicate with the help of the shell.
All right. Thank you very much. You said it's like the mediator between our kernel and also our keyboard that we use to pass in commands. We give commands to our like for our computer to receive input from us. Thank you for that. Thank you for that. Another device named Joshua. Do you have something to say?
Oh, okay. From the best of my knowledge about Shell, Shell is a user command interface that creates or builds a bridge between the user and the operating system through commands. Like a user be able you're able to put in commands which is then processed, send it to the kernel, then change it to binary, and that's binary which is then processed by the computer. So in a nutshell, it's just a user command interface that brings create the bridge between the user to be able to communicate with the operating system of the computer. That's all I know about Shell. Thank you.
All right. All right. Thank you very much. You all answered correctly. All. You all answered correctly. And that is just it. We are saying that this shell is like a program, a computer program that can help us to directly communicate with our operating system. And then we'll give our operating system some tasks to execute or some things to do for us. And there are about three possible things that can happen if we try to use our shell. For instance, we can use our keyboard, we feed it, our shell is going to read inputs from our keyboard, which is referred to as standard input. The keyboard you have on your computer or your laptop is that standard input. So when you type in commands, basic commands, or you type in anything for your shell to interpret, so when you type in such a command, then your shell is going to pass it directly. Like someone said the other time, the person used the word mediator, that is someone who is like in between two parties. So it's your shell that is the main program that is going to take in such a command that you are trying to enter on your keyboard. Then it's going to pass it to your operating system or the kernel of your computer for it to interpret. If it makes sense to it, then your computer will now give it back to the shell. Then the shell will give you an output. If the command is actually a command that makes sense to your computer, and if it doesn't make sense, possibly it will give you an error or something related to that. So that is the basic concept or the basic idea of the shell project. Like, let me say the basic. There are lots more to that, but this is just the basics. And what we are trying to do now is we're trying to play with commands. We're trying to get these commands and we're trying to pass them into our computer. So a concept we'll be discussing tonight is the I'm coming. Okay. Yeah, we'll be discussing about processes and process IDs on our so let me share my screen and display my terminal so we see into details what I'm saying. So I'm coming. Let me try to share my screen and then we try to work with processes this night. Okay, I believe my screen is being shared now. Someone can see my screen. So first things first, can someone confirm if my screen is being shared? Am I still on the call? I think.
Yes, it's being shared.
Okay.
Clear.
Okay. Thank you. All right. So this is my terminal, which is a virtual box. So I want to type in a command now. Let's just say I'm typing in a command called ABC. I use my keyboard to type this out and it's being displayed right here on my screen. And then I would use my enter button to type that in, and then you can see I already have an output right here on my screen. Let me reduce the font so you see that. You can see I have this particular output on my screen, and then it is telling me something like this command is not found. Not found. Wow. It means, okay, let me use a command. Now let's say I'm typing PWD and then it's doing something. To some people this command might not make sense, but to my terminal it's actually giving a kind of output like, okay, I understand this command, or I know where this command is and I can actually run this command. But then I use this command called ABC. I'm passing it to this my shell that is serving as the mediator between me, that is my keyboard, and also my computer. And then it's saying that this does not make sense, that is, it is not found. So this is actually telling us something, that most of the commands we have, or if it's not even most, all of the commands that we would use or a person would use on his terminal, they are all commands that are already defined somewhere, or they are commands that are already described, that your computer, your operating system knows what it means. These commands are stored somewhere in memory on your terminal, and then this my shell is going to take in this command, pass it to my own kernel. If it makes sense to it, then it's going to return whatever output depending on what I type to my terminal. Another thing you can note here is a prompt here. This guy that you can see by the left here, this $sign up to where I have a name here called Sanfrodo at Ubuntu Foca, is referred to as a prompt. You can see something like a cursor that is blinking continuously, showing that, okay, I want you to enter something, I want you to give me something, I want you to type in something so I can execute for you. If it makes sense to me, then I will do what you ask me to do, and if it doesn't make sense, I will likely give you an error message. So no matter what you type on your interpreter, it will always, at least always, it will always give you something. And like I said, it says command not found. We'll still get to a concept where we'll start writing programs to actually find what do we call it now? To find all these commands. All the commands that you can type on your terminal, they are already defined somewhere, just like how you would run a C program. You know, you just do something like // your executable name, maybe a.exe or whatever you want to run. The way you would normally do this, that is under the hood, the same process that is going on here. But don't worry, when we get to a concept that has to do with start and we adding parts, then you will understand this more better. But I'm just giving us like a preamble. When we get here, you understand more better what this error message means, that command not found. It will make more sense to us as at that time. Now we are talking about processes for tonight. This my terminal, this particular one you are seeing right now that is being displayed, is actually working, or should I say something is actually prompting it to work. There is something right there on my own that is already stored somewhere on my own terminal that is allowing whatever I have here to work. This will now lead us to discuss what we refer to as processes, and by definition you can refer to processes as an instance or execution of a program. When we are saying an instance, meaning when you spawn your terminal, for instance, let me spawn my git. I have git here. When I type git, I'm expecting git here, so I have git here. When I click on enter, then an instance, this particular thing that you're looking at, is an instance of my git program, or in this case I can say my instance of my shell, because this guy too is a shell, because it can take in input from the keyboard, it will pass it to my kernel, and then it can also return to the standard output, which is my screen. So basically we are saying that when I click on enter and then I have this being displayed on my screen, this guy here that you're looking at is what happened. This guy you are looking at is an instance of my shell program. I can decide to click on git again and also create another instance like this. So I can go on to create different instances of this particular process called what? My bash. This particular guy is having different instances. That is, you can create different processes, or that's another word or a synonym you can use for that, different processes. And you will come to appreciate this better by the end of this session. What's this thing that I'm trying to do, me trying to open another instance of my bash, and me clicking on enter and all that. So let me cancel this now, and then let me show us something. We, in our directory on my own terminal here, I have something called /bin then /bash. This guy here is actually the program that is running on my own system. This guy, it is the particular file. You can see this, what I typed here means that there is a folder or a directory on my own terminal called bin. Inside this folder or inside this directory, I'm having a file here called bash. Basically, that's whatever I have here, that's what it means. And of course, if I should click on enter right now, you might not see any noticeable change on my own terminal, but something is actually happening, which we are still going to confirm later. Something would happen, but then you might really not see that because it's not it won't be so noticeable right here on my own terminal. So when I click on enter, and then you are seeing I have my prompt again, but right now no error message was displayed and it didn't give me any noticeable output, unlike when I typed ABC and then it was throwing an error that okay, this command is not found, this that. But on typing this, I have no error, but then something has happened under the hood. Let me go on to enter inside this bin folder, this bin directory, and I'm going to show you a bunch of files that we have there. Basically, a lot of commands that we run on our command line are actually stored. Most of them, not all though, most of them are actually stored inside your bin directory on your terminal. So if I run commands like ls, you would see it will list out a lot of files or directories that I have right here on my own terminal. This command ls has the ability to do this. Now if I should run /bin, /ls, which in this case I'm saying inside my bin directory I have a file here called ls. So when I click on enter, you can see that this same output which I have here is still the same output that I have here as well. You can see all the files, the directories I have too are all still the same. This is to show us that okay, this file called ls is actually like an executable file that is actually stored inside a directory. But by default, if I should type ls alone, like typing ls alone will work. I don't need to come and specify the full path where I have the what do we call it now, where I have the executable file which is called ls, and we can confirm that by going into this directory to go and check this particular where we have this executable file. Let me see the inside, or let me list what we have there. It's going to show a bunch of files, so let me decrease the font, and then let me list what I have in my /bin directory. And then you can see we have a lot of files. You can see the color we have on these files to show that most of them are executable files. So let me go up here and look for a file called ls. Let's see if we have ls here. Obviously there should be ls because it is working. Let me go up. It's listing them in an alphabetical order. You can see we have a lot of them, a lot of files here inside your bin directory, a lot of them. Where do we have ls? F G H L I J K L. Okay, so ls should be somewhere here, right? Here we have it. Let me increase the font. Oh my god. ls should be somewhere here. All right, yes, here we have it. You can see inside my bin directory there is this file called ls, and if you should try to vi inside this file, you are going to see it's kind of like a binary code, which I from my own end I can't read a binary code, but then your computer understands what this command actually means, and that is why it is running this command, this particular guy called ls. Not only ls, we have some other files here, other executable files. For instance, you can see this one says who am I. So if I should run who am I, I'm expecting it to actually execute whatever has been defined inside this executable. The same thing with, I think PWD is also here. So let me go to where P is, just to show you where we have most of these files, that when you type them on your own terminal, it is just going to execute instantly because it's already defined here. Where do we have PWD? Okay, all right. So here we have another command called PWD, the same thing as this command, I think PS, on and on like that. Basically what you have here inside your bin directory are a bunch of executables. A lot of them are actually defined here. So let me clear this terminal now. So if you want to run any command that is inside your bin directory, you just need to specify, okay, you have your full path, you specify I have inside my bin directory, I have a file called pwd. So this is you actually invoking the file, you are calling the file, and it is actually going to run this file. When you click on enter, it is going to run this file. So you can see that and when I type pwd alone too, it is still going to work. So how is it possible that I specify the full part of the file? Obviously that should work because by default it should work the way we normally run our files, like our C files. Like for instance, if this guy were to be an executable file, I think this is a C file. So if I want to run it, I'm going to do something like ./test, right? This ./ means that my dot by default means my current working directory, right? If you have dot, it means where you are. Then I have a slash, which is my ./ which is my current working directory. Then I'm specifying the test, that is inside my current working directory I have a file called test. That is basically what this command is, and you obviously know that if I should click on enter, this is going to run, but I'm not going to run the file. The same thing is happening here. You can specify the full path to an executable. All these commands that we work with on our shell basically are a bunch of executables. They are files that are already defined. You are not the one that actually wrote this pwd, or maybe you defined it. No, you are not the one that did that. By default, when you install your own command line, your terminal, it has all these files there. the installation package that is already put inside this folder called /bin. And this way you can run your commands. This method is what we call the absolute path, you specifying the absolute path. Let me confirm if I'm still on this call. Okay, so this is you actually specifying the full path to such a command, and this is you typing the command by itself. So this should actually tell you something. If you are writing your own shell, you should be able to write it in such a way that if someone should specify the full path to the file, your shell should be able to execute such a command. And if someone doesn't even specify the full path to the file, then your shell should be able to look for this file wherever directory it might be defined or where it is stored, and then it is still going to run it. But I'm using a standard shell now, so we should try to design our own shell to also follow this syntax. To follow, it's not even a syntax, it should follow this pattern. It should work the way the shell on your own terminal would actually work. So you should be near it, even if not 100% working like that, but it should be near, like to a reasonable degree. It should be near. The same thing, your commands, not only can you type the full command, you can also pass in arguments, or you can pass in optional parameters to your commands. For instance, let me run with absolute path. We have my /bin. We have ls inside the bin directory, right? So we have that there. So sorry for that. So we have a file called ls inside our /bin directory. So when I click on this, it's going to list my files. I want to do this again now, and I'm going to pass in a flag called -l, and I'm going to click on enter, and then it is listing my files in a different format. By default, ls would list your files, but when you now pass in a flag, this flag has some things we do. You can just check your manual and type man ls, and you're going to see, okay, what is this flag doing? What is this going to do? So this is showing us again that your shell cannot only take simple commands like this, it can even take commands, and then you are going to pass in arguments to it. Like I said, whatever shell you are trying to build should be near the one you have on your home terminal. Should be near it, even if not 100% like it, but it should be near. So how is this thing actually working? How is it working? You might be wondering, what exactly is making all these things to work? How is our own or my own terminal interpreting this line? How can it know, okay, you run this, then you pass this to it? You might be like, okay, this is actually, I specified the full path. If I should run this command without specifying the full path, like where the file is located, this is my ls file, it is still going to give me the same output. If I should type ls alone and with my -l, this particular command is still going to work, giving me the same output. You can see that, right? Exactly the same output as when I specify the full path where the executable is found. Not only can you specify commands like this and display them on the output, another thing a shell can do is that you can redirect these outputs and store them in another file. Or you can say, no, I don't want this output, whatever output my own terminal is going to give me, I don't want it being displayed right here on my screen. That is the standard output. That's your screen. You don't want it on standard output. You want to redirect it to another output. You can even specify that right here on your own command line. You can use commands like, okay, let's say we are doing ls -l. You can use this, your redirection symbol, which is this guy, to redirect output. Let me increase my font there. Okay, let me just clear the screen. All right. So you can the output of this command, you can redirect it into a file. Let's say you are naming it ls.txt, and then you click on enter. This command has actually executed, but you are not seeing an output here. Why? Because you already redirected the output. So this is showing us another thing our shell can do. One, it can take simple or basic commands. Two, it can take optional arguments to our commands. Three, you can redirect using the redirection symbol. You can redirect output for it to actually store it in any file, and if the file doesn't exist, it can create the file by default. Okay, I didn't even show you that. Before, I didn't have a file named ls.txt on my command line. I think I should have it now. Where is it? The file is not being displayed here. Okay, this is it. I didn't have it before though. Let me run this command again and pass it to another file with another name. Let's say LA, and then let me do ls. You are going to see that it would create this file by default. Where is it? Here. This is it here. So you can see different things your shell can do. So if you understand these things, you actually need to know what your shell can do before you even try to actually start writing it, because if you know, it is what you know, you'll be able to code. If you don't know it, how will you be able to code it? So you should actually know the kind of functionalities that are applicable or that you can get from your own command line. Only then will you be able to write your code to work in a way that is similar to this. And you, of course, apart from this, you can even do something more advanced. And when we start discussing concepts like piping, you are piping in a command and you feeding it to another command, or you trying to echo something, or a command you piping it to an executable and all that. All those ones are even advanced stuff that you can even do right here on your command line. So basically, all what I've been saying since is just that you should understand your shell. You should know what is happening. You should know how it works. Then you now try to make a clone, and you try to actually define and write your own shell to work in this same format. Remember that we did a project on file input and output. I think that was the last project we did before we actually started this particular concept called simple shell. So please take that concept seriously, your file IO. If you do not understand it, maybe you might want to go back to it. And it is only that concept that will help you to be able to actually add this type of functionality to your own shell when you are trying to code it live. I feel there is still something I want to say, but okay, good. Yeah, another thing is this. Another functionality that can likely occur on your own shell is when you have this particular guy called hash on your own shell, and then you enter something like, let's say you have something like ls, and I'm entering that and nothing is happening. Or you might think, is it because I have a space? Let me delete the space, and then you can see nothing is happening. So this should actually tell you something, that whenever you have hash as shall I say the first argument right here, that is the first argument you are entering on your command line, such a command that you are entering after it, or your shell is basically not going to do anything. This hash is a comment, and comments are ignored, right? So you should know when you are trying to write your own shell, you would have to add this type of functionality to your own shell. Like I said, we try to write our own shell for it to behave the way standard shells work, even if not 100% up to standard, but then something's very near. Another functionality you might notice maybe while playing around with your shell is this. I have commands like pwd, then you have a semicolon, then pwd, you have another semicolon, then pwd. This is pwd is going to print my current working directory, right? So I'm typing it here 3 times, 1 2 3, and then I'm clicking on enter. You can see that it executed them individually, the first one, the second one, the third one. This is the same as me typing it one after the other, right? And then it's still giving me the same output, right? But just that everything, I typed all the commands at once. So again, this is telling us another thing, another functionality that we can likely get on our own shell. So please, all these points, just take note of them. By the time you get to the real project itself, you'll be asked to actually implement them, even things that are more advanced than this. But for the sake of this class, we would be discussing about I'm just giving us like a general overview of how the shell, or what your shell can potentially do, apart from normal basic commands that we know, with typing ls, pwd, and other basic stuffs. Your shell can do things that are even more advanced than that. Now, discussing about processes. For like we said, this particular guy that I'm running is a process. Let me see, can I actually get the okay. Let's say I want to cancel my shell. Good. Can you see? I tried to actually cancel it, and then it's telling me processes are running in section blah 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 blah. It's giving me a message. That is this particular instance, that is this particular terminal that I have here, a program is running it, and then it is like an instance of such a program. And then you can see it's telling me this, this, and this. For this, it has this. Then it's telling me some messages. It's displaying some messages right here on my terminal. The main point I want to bring out here is that this particular instance that I'm running is actually a process of should I say another process this time around. So tonight we'll be discussing about processes, we'll be discussing about parent process, and we'll be discussing about processes themselves and also parent processes as well. So to begin with, I would be let me create a directory called simple shell. Let me create a directory called simple shell. Then let me cd inside it. I believe I'm still on the call. Okay, so let me create a file called process. Am I still on the call?
You are.
Okay, yeah, I believe I'm still on the call. Okay, let me flip through the message.
Yes.
Yeah, the person that man is back. The person that raised his hand
Yes, you are on the call. We can hear you.
Okay, please let me check the recording. Let me confirm if it is still working. Okay, 32 minutes. All right. Okay. So let us.
Someone you're echoing.
I'm echoing.
Echoing.
Okay, can someone else confirm if I'm echoing?
That's not.
Maybe
No.
it is network.
No,
You're not
right.
echoing.
You're not.
Seems good to me.
It's clear.
Okay. So we'll be starting with writing our code. So since we'll be printing something to the standard output, so I want to include my standard input output. Okay, I should put O there. .h. Okay, someone's hand is raised. Okay, maybe that's a message. Now, let me have two terminals. Okay. Okay, good. cd simple shell. Okay, let me see. Oh no, I want to be sure this file is here. Okay. All right, now if you want to actually know these processes, there are some commands that we can use to actually get the process ID. I'm sorry, please let me check the messages. Things on. All right, so we have two commands that we can use to this effect to help us to actually get the process that is actually running a file. That is, we are trying to run a file, we can get the process ID of such a file, that is the instance in which that file is running. And the reason why we need to get this we would know later. So to do this, we would need to in fact, should I check the manual for that? Let us check the manual for those commands before we actually write them. Let us man the manual to check is man to get PID. Let us see some things about it. Then this is the manual. Get PID, where is it? It says that what? It returns the process ID of the calling process. Basically, that's what it does. It returns the process ID of the calling process. So it is defined in these headers. Then it has a return type of PID underscore T. This is a special data type in C to return process IDs. You can see PID, process IDs, so underscore T. Then get PID, it takes in no argument, which is void. Okay.
Please, can I ask a question?
Yes, what's your question?
Please, what does man 2 and man 3 stands for? Man 2 and man 3. What does it stand for and how is it used?
Man is basically a manual. Your Linux programmer's manual. So, for instance, there are some commands that you would get in man 2, or should I say commands that they are separate, they are the same command actually, like they have the same name, but then different ways to use them. For instance, there is this command, I think, for printf, or the whole family of printf, or write. Yeah, I think for write there's something called man2 write, and there's another manual for write, just write itself. So the 2 and the 3 there is just specifying the particular manual you want to check for. Basically, my man2 gets PID. Possibly, maybe there's another I don't know, but maybe there's another.
Okay, so if I understand what you're saying,
Yeah.
you're saying that the commands are saved inside the manual.
No, man2 is different from, if you have another one that is man3, it's obviously different. It's different. For instance, this particular guy, man2 gets PID, is defined in this header. Let's say we have another one, maybe man3, that also has the same name, or maybe something similar to get PID, maybe get PIDD, or anything of this nature. It might be defined in another header. Most times they are different. So you just need to know the particular command you are searching for and the particular manual to get it. But for this one we are working with, is actually defined in 2 get PID. So you have to man it out.
No, I don't know if you understand where I'm coming from. I want to know if the commands are saved inside the manual.
If the commands are inside the manual, well,
yes. Because let's say if there are some commands that you can find in man 2 but you cannot find in man 3, maybe there are some commands that you can find in both man 2 and man 3.
Okay,
are the commands saved inside the manual?
You know, your Linux programmer's manual, I think by default it's, maybe, I don't know if you installed it, or by default it comes with your terminal. The commands are not actually saved inside manual. The manual is just telling you what a particular command is doing, where the commands are defined, or how you can actually use them, because they are defined in these headers. So what you should be concerned about, what the command is doing, should be what do we have in these headers, which obviously is maybe part of a static library or part of a dynamic library, or anything you have in your slash that is usr slash whatever, I think static libraries or something like that. That is where you have all these guys, these headers that are defined. But what exactly is the manual doing? The manual is just telling us what a particular command is doing. Like, it's just telling us a brief description. It's not all commands that would know what they are doing, so we have to actually check the manual for them, just like a guide telling you what it is doing. But the specific commands are not actually defined inside the manual. It is not the manual that is giving us how to like how it will behave. It's not the manual that is doing that. The manual is just telling us what it will do, but the commands are not defined in the manual. They will be defined in whatever headers that we have here.
Okay, so it's just the description of the commands.
It's exactly just a description to help you know how to use it. Yeah. So basically, it's telling us now that if we want to use this command called get PID, we would need to likely include these headers, and then it says that it gets process identification, and it says that it returns the PID of the calling process. That is what it returns. If you use get PID, it is going to return the PID of such a process. And basically, when you are uh in a file, you are trying to run a file on your command line, a process would be created for such a file. That is the instance of execution of such a command, such a file, not a command this time around. The process of execution of such a command would be, it will have a unique process that will be used to identify it. On our terminal, we have something called the process table that has a list of all the processes or instances that are running. That is why if I should spawn my terminal and I want to like cancel this terminal, it's going to actually give me that okay, a process is actually running, which is this current terminal that I'm running here. If you try to run a file, an executable file, it will have its own process that will be created for it. It is such processes that will uniquely identify, okay, you are running this particular command at this instance, and when the command has finished executing, then it will be removed, it will be deleted. That's after it has ended its execution. But if you want to know the process of a command that you are running this time around, when we are trying to run our file, our C file, then this is the type of function you would want to call to actually achieve that for you. This is what you want to call. So it says that it returns the process ID of the calling process. Why this other one called get PPID returns the process ID of the parent process, of the parent of the calling process. The idea of parent comes when a process creates another process, or an instance of a process is running on another process. Let's say, for instance, now, if we are trying to run a C file here, let's say I have an executable on my command line. Let's say the name is ./exe, and I'm trying to run this executable. I already have a process running, which is my own simple, this shell itself, this is my terminal, it is running. And then I'm trying to run this command. This command that I'm trying to run would have to be a child to the current process that is running, which is my vagrant. This is my terminal. I told you that a process is running. If I try to cancel it, it's going to give me the prompt that a process is running. And it's the process that is running. All processes, they have their own IDs, unique IDs that you can use to identify them. All processes. Therefore, if another process is running as a result of a process that is already running, therefore the new process that is running would have to become a child to the process that was running before it, that is, which is the instance of this my vagrant. So basically, you can get the process. When I run this file now, I can get the process of this file, and then I can also get the process of the instance of my vagrant that is helping me to run this file. Because ordinarily, without my vagrant, it would be so difficult for me to just maybe type ./exe on my, let's say, my file manager and say I want to run it. It won't be possible that way. But then with my own vagrant, or with this my terminal, I can use that to run it. And my terminal itself is a process. Whichever file I'm trying to run, or whatever file I'm trying to run, is also another process that is running on my terminal. So my terminal will now serve as a parent process to this new process I am trying to run. So we are told that we can get the process ID of any process that is running using this our command. That is, we are going to actually include this command in our C file. Therefore,
Can I ask a question?
Yes, you can go on.
Okay, thank you very much, and I really appreciate this teaching. Please, can I say that the prototype for this program are found in the manual, or are we going to still declare, are we the ones that are going to build our function and form our prototype? Because from what I'm seeing here, when you run the man to get command, I've already seen that a prototype here is defined, this function, that is PID underscore T get speed. And I think it's going to be like that for all. Now, so the
Yes.
question is it that they have given us prototype but found inside the manual? So when you run the manual, you see the prototype and the description, or you ignore it and then still run our function, then create a prototype for ourselves. That's the question.
Okay, if I heard you correctly, I think the question you're asking a two-in-one question. I will answer the first one. It says you're asking about these prototypes. Yes, this particular
Yes,
function
yes.
has been defined inside these prototypes. So that means if you want to actually use this function, if I do not include these prototypes, then I'm going to get an error. By default, when I type get PID inside this my C file and with these prototypes included, therefore it is going to run because my compiler will understand that okay, get PID has been defined inside this header, so it is going to check it out and it will know what it is meant to do. But if you want to use get PID without defining without including these headers, then that means you would have to write the function. You are the one that would know how you are going to define it by yourself. But why go through that stress when you already have a system function that will do that for you and will get the process ID of this particular instance you are trying to run and even the parent process ID. I don't know if that answers your question.
Okay, yes, I really appreciate. So another question is just like, is it that they will provide the prototype like this for all? Like when we run a command, we have prototype for all the tasks, 0, 1, 2 down. I don't know if you understand me.
Okay. Like inside your main.h or
Yeah,
shell.h file. No,
yeah,
for
it's
these
like there's
particular
like an
functions, you don't need to declare their prototypes. You just call them because they are already included here. You don't need to
okay,
declare this. No, I don't think you need that. You don't need to do that. I don't think you need to do that. Just like you wouldn't declare the prototype of your printf or scanf when you want to use them. You don't need to create a separate main.h file and declare it there. Then you now come and call it in your main.c. You don't need to do that. You don't need to do that. It's already included here, so you don't need to do that. It's only when you want to
okay.
use your
Thank you
user
very much.
defined functions you'd have to include their prototypes in your header in your header file. So basically, what we need to know again is that this guy would return the process ID inside a special data type called PID_T. So I have to declare, let's say, a variable that is of this data type, right? So I'm just going to type that in _t. Then I can give it any name. I can just say process ID or something of this nature. _ID. I can decide to give it this name. Then I know when I call my function, let me include the header so I wouldn't get an error when I try to run my file. So I'm just going to include that right here. So it says sys/types. So I will just include both of it, even though if I include only unistd.h, it's still going to work. But then just for the sake of this class, I'm going to do that. Okay, so I've included both. Then I declared a variable here called process ID. That's the name of my variable. Then I can now say my variable now would be equal, so it can store whatever this function is trying to return, basically. So I can say it is equal to get PID this. I don't need to pass in anything to it because we are told from here, the prototype, that it is a void function. It takes in no argument. So you don't need to pass in a variable or anything. It just has to be opening and closing brackets, basically. So when I do this now, this my get PID would store the process ID. When I run the file, I mean it's going to store the process ID because that's what get PID will do. It's going to return the process ID of this particular function. So let us do that and let us see some things that would occur. So let us try to print out to the standard output. I can say that my PID is this, and I'm going to use my %u for unsigned. Yeah, I didn't mention IDs would always give you positive values. They can't be negative. Like processes, their IDs are always positive. So I use my %u. Then I want to add a new line like this. Did I close this? Okay. Then I want to specify what my %u is. I want to print out process _id, which is this variable. I want to print it out. So when I do this now, it says printf is going to print my PID is _u, which is unsigned variable data type, then with a new line, then I'm expecting this type of output. So I'm going to exit this interface, save my file, then try to run. I'm going to save my file, and I'm going to run it, and then gcc the name of my file, which is process.c. Then I want to save the output in a file called p. So I click on enter, and it says that what, no such file or directory. Okay, I think I have a typo there, so I'm going to retype it, uni.std. I typed unit, it should be uni.std.h. I think it should give me the correct output self. Okay, it says no such file or directory. It's not even telling me the correct one. So it should be uni.std.h, just like we've seen it from the manual, right? I was the one that did a typo there. So I'm going to resave now, and I'm going to rerun this particular. Okay, no errors. And then I want to run my executable file, and then it printed something out to the screen. It says that what, my process ID is 258032. It's giving me this kind of output, that this is the process ID of this particular file that I'm running. Like I said, when you are running or you are trying to execute a program, it would have a process ID by default that will be assigned to it. It is this process ID that can be used to track this file and to know like details about whatever instance or execution of a program. Let us do something. Let me try and run it again. On running this file again, it's giving me another type of ID. Okay, let's run it another time. For the third time, yet again, I'm having another process ID. PID means process ID. So now this is telling us something. Okay, do I have okay, this is telling us something, that processes or IDs would always change.
Just hold on a bit, it's coming. Just trying to fix up something.
On each instance. That is, when you are running this file, the file that you ran here is actually different. It's still the same file, but then the process is different from this one, and it's different from this instance of execution. This is what is happening. By the time I did my .4/p, which is my executable file, in memory, it was allocated a process ID that will be used to track this file. After this file has finished executing at this point, where I have my prompt again, the process was deleted because it has already finished executing. The process was deleted. So that's the reason why I decided to run this file again. Please, am I still? Oh, sorry, I didn't even know I was muted. Wow. Am I still sharing my screen?
No.
No.
Sorry. Someone just messaged me that. Wow, I didn't even know that. Maybe it was my network. I'm so sorry for that. I didn't even know. Okay. So I was actually saying that I ran this my executable 3 times, and yet I'm getting different processes. The reason is because each of these instances where I ran this my executable, they are allocated different processes, meaning that the first time when I ran this file, it was assigned a process ID in memory, and after it finished executing, it was removed, it was deleted from the process table. It is gone. I mean the instance of execution of this program. You know, when you are trying to run a program, it is going to actually get loaded into your RAM, right? This particular executable file will get loaded into your RAM. It is now that your kernel or whatever is assigned to actually run this file, maybe your GCC compiler or whatever, will now use. It is that copy that it's now going to use, and it's now going to run it. Then after it has finished running it, then it's going to remove it. Obviously, it needs to free your memory. It needs to free memory, right? So it is going to run your file, then it's going to remove it from the process table. So that is why, as at when this file was added or included in the process table, it has this process ID. When it finished executing, it was ripped off. It was removed. So when I ran this file again, it has to pick this file and load it in memory. it can't be the same process ID because this one is gone. The instance of execution is gone. It is gone forever. So this is another process at this particular point that I'm running. The same file but different processes or different instances. I'm actually running the same file but it's at different instances because the process table is like, should I say, very, a table that keeps track of processes or instances, things that are running. If I should delete this terminal here, right, and I click on enter, this terminal is gone. It is gone forever. Like this instance of execution of this terminal, it is gone and it is gone forever. It's only, I can't even recover it. I think it is gone because it is already off the process table, so it is gone. The same thing is happening here. If I should run this file after it has finished executing, it is gone and it is gone. That is why when I rerun the file,
Hello,
I'm getting
Samuel.
another process. Yes?
Samuel, please, sorry for interrupting you. Don't be offended. Is it on record? Are you recording this session?
Yes. The call is being recorded.
Okay.
For real, you interrupted to ask if it's on record.
So, the same thing for the third instance of execution as well. It is going to generate another process ID for it. So just view this as when you are running a file, each instance of execution of the file would have different processes, just to show you that it is not still the same process that was running here that you are trying to rerun. This one is gone and it is gone. This is another instance and this is also another instance of execution. I don't know if we are clear with this particular concept, or it's kind of confusing. If you have questions, you can just use the raise hand button. Mr. White, where you dey? Can you raise up your hand? Okay. Oh, what did I just do? Sorry, I think I just did something now. Wow. What did I just do? Okay. Someone's
I think
hand
you
is
can
up.
stop sharing and share again.
Okay. Vivian, you want to ask a question?
Yes, I want to ask a question.
Okay.
So my question is, since if the process is stopped, the ID is terminated and lost forever, what's the main reason why we create, or why does the system create the PID in the first place, the unique ID?
Okay. I mentioned earlier that these IDs are used to track processes. Your system needs to take note of how many processes are running. And it has limits actually. It will not be good if your computer is running too many processes at a time. So at times when we have a lot of processes, it has to terminate some. Like it depends on the memory size or the RAM of your CPU. When a lot of processes are being loaded, it can start hanging or start going at a slow rate, stuff like that. But these processes or these IDs, unique identifiers, are used to actually track the processes. It is like, should I say, an identification mark that will be attached. Your system is not seeing this as maybe ./p. No, it is seeing this as, okay, there is something running and the name is 258071. So you can just view this as the name, the particular instance of execution of this file as in the memory of your computer. So this is the name, and the name is uniquely identified by this particular number that it is generating. Now, if it wants to remove this guy from the process table, it is just going to delete or completely terminate. There are some system, or they call it signals. For instance, you would see maybe by the time you are working with your shell, you start mentioning things like exit success. I think on the intranet, you'll be asked to actually learn about signals and calls like that. Signals, I think mantle signals, something like that. You would appreciate this better. Why you actually need to have these IDs, because it's these IDs that will be used to track whatever signal or exit status or exit success or failure or whatever that your particular instance of that your shell is actually running. But our IDs and our process IDs for the context that we are discussing now, we just want to make it clear that whenever we are trying to run or execute, or when we are running any process, that is, we are running a process, it's going to get by default a new ID. Each time you are running it, is going to get a new ID. That's just the point we are trying to make from here. Another thing we want to discuss about is the parent process ID. Just like we saw from the manual, right? Okay, someone's hand still up. Okay, that's a message.
Good evening, everyone. I just have a suggestion. Can we please have a question and answer session, maybe after you're done with the class? Because along the line, a lot of questions will always come up. And if different people keep asking questions, we'll tend not to later achieve the main purpose of this class.
Okay.
So maybe after you're done with the lecture, everybody should, if you know you have a question, you can just put it down first. Then maybe afterwards, we can ask our question. Thank you.
All right. Thank you for that suggestion. So you can use the chat box to drop your questions if you feel like you might likely forget before the end of the session. So this is the second thing we'll be talking about for tonight. It's called the get PID. Basically, it says that it returns as well. It returns the parent process of the ID. It returns the parent ID, identifier of the parents of the calling process. What is a calling process? The instance of execution of, in this case, our file called process.c. This is our file. The instance of execution is the calling process. So it is going to return the parent process of this ID. That is the instance where this file is running on. That's basically what we are being told here. So once again, I'm going to declare another variable of PID underscore t, because that is what it returns. My get PID returns that. It's also a void function. It takes in no arguments. So I'm going to declare another variable called PID underscore t. Then I'm going to say parent underscore process I, or parent process underscore ID. So I'm going to call my parent process underscore ID. I'm going to say it is equal to get PID as well. No, get PPID, sorry. It has PP for parent process. So I'm going to terminate that with a semicolon. Then the same time I'm going to have another printf here. Printf my parent process ID is this, then an unsigned integer with a new line. Then I'm going to call this guy called my parent process underscore ID. Alright, so let me assume this will, okay, I should terminate with a semicolon, not a colon. So let me assume this is correct. So, or let me come here and say my parent process ID, to make it even more descriptive, is this. My parent process ID is this. Then my process ID, so child, is this. Okay, all right. So I'm going to rerun my file. I'm going to recompile, and then no errors. So I'm going to run the executable again, and then we are having a process ID, which is the child now, which is this instance of execution of this my file called ./p, an executable. So the ID of execution of this process is this number we have here, and then the parent process, which in this case is my terminal, because my terminal that is running this file, I'm running it on my terminal. So by default, my terminal will be the parent process of this file. So the ID of the parent, that is my terminal, is 218.708.704. So I want to rerun this my executable, and of course, like we said, your process ID would always change, right? So you can see this here. The parent process the process ID of the child, which is the instance of execution of this file. Another process has been created because this process has already terminated. So this is the new process now, and then we have another new ID. You can see something unlike the first, unlike the process ID of this file that is changing. The parent process, which in this case is my own terminal, the process is not changing. It isn't changing. Let me rerun for the third time. Still constant. So this is actually telling us something. The parent process of the parent process doesn't change, whereas the process ID of the process itself, that is this process, is going to change, but the parent process doesn't change. So we are asked to use this other command to check something, this echo space with a dollar symbol, and when we click on this, okay, no, let's see, it should be a double dollar symbol, not a single. This one will only echo this to the output. So when we do something like this, we are getting a process ID. Let me rerun this file, and here we have it. You can see the process ID, parent process this time around, which is my vagrant, actually tallies with this. So this is one way right here on your command line you can use to get the parent process of any file you are trying to run on your terminal. In essence, echo dollar dollar is going to give you the process ID of this terminal, but the process ID of this terminal happens to be a parent to whatever you are trying to run on your terminal. So by now I believe you should understand the clear difference between a parent process and also a process itself. A process, any process can become a parent provided it is running something. If you are running something, you will automatically become a parent. Like if something is running, let's say under you, or just like when someone gives birth to a child, you become a parent. That doesn't mean you yourself, you are not human again. So for the fact that my terminal is a parent process doesn't mean it is not a process. It itself is a process, and my terminal itself has a parent too. Obviously there should be a parent, because my terminal can't just be running, maybe it's running on the instance of my CPU or anything, but this terminal wasn't on my computer when I installed it. So obviously when I installed it, it is a process that is going to load it in memory for it to start running. So obviously it would be reasonable to believe that my own terminal would also have a process. But what we are seeing right now is that my terminal happens to be a parent to a process that is running under it, that it is running a program. Therefore it has become a parent, but it also has its own unique ID. So we've been able to establish the fact that processes do change only when you run such you create another instance of such a process. Like in this case, we are rerunning our executable, and then each time we are rerunning it, the process is going to keep changing. Now I'm going to do something now. It seems as if this guy isn't changing, but you can actually change this guy. How? Your parents' process, you can change it. How? The same way we change this process. Like I said, all of these things we have on the screen, they are processes. My executable file is a process. My vagrant itself is also a process. So if I can actually change the process ID of this process by rerunning it, I can also change the process ID of my vagrant by rerunning my vagrant. Basically, that's just the simple logic. If I rerun my vagrant, that is the instance of execution of this my virtual box, that is the bash, which is the program that is running this particular vagrant, the terminal I'm having here. If I rerun it, obviously the process ID should change. So that is what I'm going to do right now. I'm just going to rerun my bash, which is my /bin/bash, right? So we did this earlier at the beginning of this session, even though we might not really understand what this means. Like I said, it's not going to give you any output when you run it. It's just going to, I press enter. It's not going to give me an error message. It's not going to behave as if it's a correct command. It's just going to just run. But what is actually happening here by typing this command, what is happening under the hood is that I am restarting or creating another instance of my bash. The same thing I'm doing here me recreating another instance of my executable called P. It's also the same thing I'm doing here. This means dot forward slash. Dot means my current working directory. Slash means what? Slash is like a folder to specify a directory. Then it means P is in my current working directory. This is what this basically means. I'm running a file. The same thing. I have to run this file too, but I'm specifying the full path to my file. So when I do this now, I've created another instance of my what? Of my bash. And when I do my echo $, echo $, like we said, it's going to give you what? The process ID of this particular bash that is running, right? So when I do that, you can see the process ID has changed as against what we have here, which didn't change earlier. We did it, I think, twice. Okay, we did it only once though, but I ran it from here again, and then we confirmed that it doesn't change. Why? Because I haven't reloaded my instance, or I haven't reloaded the file that is actually currently running on my this particular vagrant. This terminal we are looking at, this is the file running its bash, and it is inside a directory called /bin. So when I do echo $, like multiple times, it is not going to change. Why? Because I haven't created another instance of this file, unlike this one that I'm running every time. And every time I'm running it, I'm recreating another instance of the file, right? ./p. When I keep running this, it's going to keep changing. The process ID of this file is going to keep changing. Why? Because I'm rerunning it. The same thing, if I'm rerunning my bash, it's going to keep changing. So if I'm doing echo $, echo $, it's going to keep changing, just to show that processes will change when you create another instance of such a process. It is, or no, should I say of such a process? Yeah, I can say such a process. When you create another instance of such a process, it is going to change. But by default, who would want to start running bash? What for? Why do you need to do that? So that is why most resources might tell you it doesn't change, but in the real sense, it changes. If you try to rerun such a file, it is going to change. But most resources will tell you parent processes don't change. Any process can change provided you are running it multiple times. Anytime you run it, it's going to get loaded. The former process running is going to get terminated. A new process will be loaded in memory, and obviously a new process will get a unique ID. So that's why if I keep running my echo $, which is this guy, it's still giving me the current process of instance of my bash. Then when I run my bash /bin/bash and I press enter, then echo $, why is this command not coming up? What's going on? So you can see it has changed, right? I want to run it again. What's going on? /bin/bash, then echo $. It wants me to keep typing. You can see that, right? It will keep changing because I am rerunning my bash. But like I said, you do not need to come and run your bash. You don't need to do that. Let a single bash actually run your files. So you can create different files, like you can run different executables at a time. Let's say we have here, I'm running /p. Let's say I have like 5 files here, right? And inside the files, they are all doing what I have inside this my code. Each of these processes, if I run them, let's say I compiled a file called process.c inside P, and then I have another one called maybe example.c, and about 5 of them like that, and they are all giving me the process ID and parent process ID, right? If I run all of them at once, each of the files would have their own unique IDs, which is this guy. The get PID is going to give them their individual unique IDs, but their parent process is going to be the same. Why? Because all of the files are running on the same instance, this particular instance of my bash. Like all files, basically all files, they are running. And how can you use your program to get the process ID? You have to call this system defined system calls that are called get PID and get PPID. Get PID, like the name implies, is to get the process ID, while get PPID is used to get the parent process ID. And you have to include this header, especially unistd.h. That is where the prototype of all these functions, these void functions, have been defined. So this basically explains the concept of processes and process IDs, and how to the concept of parent processes too as well. And the maximum number where these guys are is actually defined in a file. Like if I'm saying the maximum number possible for this your process ID is defined in a file, you can view it into your /proc file directory sys system, then your kernel system, then your kernel, then your PID max. So if you view into this file, it is going to give you a number. Please don't edit it, because if you do this, it can potentially affect your system. Or in fact, it's best you just cut it out. Because what I'm doing here is not advisable. I shouldn't edit that guy. So I just did cut. Please, can you help us mute that person? I just did cut, then this file means inside my proc directory, my sys, my kernel, then I have a file here called PID max. It's going to give me the maximum number possible any process ID can get. So from there you can see all right, like this number, like if you start running your processes here, let me run my file .4/p. No matter how many times I run it, I can never get a negative number for a process ID. It will always be positive digits, and I cannot get a number that is bigger than this my PID max. Like this should be 1 2 3 4 5 6, about 419,000, no, 4,194,304 as the maximum number any process can get. And you can see all these individual numbers cannot be up to this. So basically that is just showing you, and if you edit this file, your system can start behaving funny. So please, you have no business with this file called PID_max. You have no business with it, except you absolutely need to edit it, maybe to reduce the number or to increase the number, or if there's a reason you have to do that, though. But if there's no reason, just leave the file and let the file be. So this basically summarizes the first session of this our 5-day series on the simple shell concept. So today we've been able to give us a brief intro to what a shell is and the different functionalities we can get. We didn't exhaust all the functionalities, though. We didn't exhaust all, but I just gave you like a preamble of how a normal shell would work. We talked about we typing basic commands. We also talked about we typing basic commands with optional flags. We talked about we typing basic commands with optional flags and we redirecting the output to another file, and if the file doesn't exist, it is going to create that. We did that at the beginning of this session. We also discussed about we typing commands and actually putting hash in front of the command, and we practiced that, and the command did not run. We did that again, the command did not run, which is telling us something about how our shell works, right? From there, we also discussed about we typing commands, and then we put in a semicolon, something like you typing PWD, then you typed in a semicolon PWD. We did something like this, and we saw the output. So we said, okay, our shell has this functionality. There are also other functionalities that you have in your shell, which we didn't discuss about. So on your own, you can still make your own research, and try to learn how the shell works. Things that would likely happen. If I do this, what will happen? If I type this command, what will happen? What is file not found error? What is happening under the hood? But today, we've just discussed basically about processes. How will you apply this to making your simple shell program? We are going to learn that. That should be, I think, in 2 days' time. Yeah, that is when we'll now start creating processes. Tomorrow, we'll be discussing about argument vector and argument count, and also about getLine function, and then we'll also discuss about string talk tomorrow as well. So we'll likely write, we'll do something tomorrow, discuss about this argument count, argument vector, and all that. I think that's what we'll be discussing tomorrow. Then next tomorrow we'll be discussing about creating processes, where we'll discuss about the fork, system call, the wait and the sleep. Then after that, the day after that, we'll be discussing about the exec v, how to use such a command. Then we'll now create a shell. Like we are going to together, we are going to create a shell because by then you already understand all what we need to create a shell. That's like in 3 days from now, or I think is it 4 days from now. We'll now create our own shell. Am I still on the call? Oh, I'm having network issues.
How do we tackle the history part of shell? That's that arrow key. I've been thinking. I'm trying to. Do you understand what I mean?
No, we don't.
I mean, when you click the up arrow key to go up.
Somebody check your DM.
For now, I can't actually say how to recall the previous commands, or maybe there's a place it is storing it. I can't say, but of course.
How about completion of text?
I actually can't say
of a file with tab.
Yeah, I get your point. Let's say process, then I'm clicking on tab. I can't say it
because those ones, when you do them, you don't actually see this thing. As in, I don't know how to put the question, but what I mean is, when you press the arrow key, it won't actually type anything on the screen. You get?
If you use arrow key, it would actually print out something, but it will be undefined. It will likely be a very weird symbol, something like all this this symbol, something like this. This is what it's
like. No, I mean that's up and down. That's cursor. Not
okay, cursor. Up and down will not display anything.
Yes, your direction key. Yes.
What about the left and right?
Yes.
What about the left and
right?
No,
it means up and down. Up and down.
I mean up and down.
Yeah, I'm asking.
Normally in our terminals, if you want to go to the previous this thing command, you use your up key. So I'm still trying to figure out, since we are building a simple shell, I'm still trying to figure out how, if I want to replicate such feature in my own shell, how I would do that.
Okay. Yeah, actually, in programming, everything is possible. There will obviously be a way to do that, but for now, I don't know how to actually recall previous commands. The only one I know of is for your changing of directories, where you can change to the previous directory and actually use such a feature. But for your up arrow and all that, I don't know. I also know of your redirection symbols when you want to like direct output to a file. That's where your file IO project comes in, and you'll be able to appreciate that better. I'm aware of that one. But for recalling previous commands, your up and down arrow, that I do not know for now. But you can always make your research and try to figure out how you can go about that when you start building your own shell. But that should be part of the advanced tasks. It's not part of the mandatory tasks.
He should do his research and come and teach us in our next session.
I believe before doing research, you have to just think through a problem and at least have an idea based on what you have been taught or what you have learned before. If I say, let me just picture this thing, I will say it might work something like a cache. You know what cache? Catching a memory, and that's any command you have run is stored somewhere. Now, let me not call it an array. This one array is fixed. I don't know, but it's kind of it's a data structure. Yeah, it's structured. It's stored somewhere, like almost like a stack, where it will be recalled. The last one that went in, you access it first. I don't know if people have done Stacker. I'm not sure if I've done that. Sorry. So the first one goes in, second one goes behind there. The last one you want to go get it back, you get it from the last one, which I believe when you press your up arrow is the last command you get back. So it's that kind of thing. That
Yeah,
is how
last
it
in,
works. So now it's now to
last
implement
No,
in.
no.
last in first out.
The
Okay.
area I'm having problem is the fact that uh, if I press CD, I'll see the CD I press. If I press LS, I'll see LS. So then if I press something like the arrow key, there is no this thing that will display on the screen before it as in maybe running the command or something like that. Do you understand what I mean?
Yeah, I get your point.
All those things will be implemented. There's nothing that will work that was not coded or implemented or programmed. Don't expect anything you do not program to work. That's the thing. It might be difficult to implement these things, but I'm just giving you an idea. Nobody has taught me. This is the first time I'm even thinking about it as if I said it. But I have the habit of
All right,
anything,
no.
any problem that comes, I think through all the things we have learned and see how it can be applied. So I can just give you a
There's no
rough.
problem.
I believe this is how it is it's structured, but how to now implement it now might be not be so easy. To now implement maybe how to get I believe it's a stack last and first out. How to if you do it the normal way you're doing others, you might still be getting errors. So one you know now how you do it when you start implementing, you'll now be seeing more challenges or more stumbling blocks on the way, that kind of thing. So I believe this is
All
the
right, thank
rough idea. It's good you have an idea first, yes, before you start doing something.
thank you very much. Thank you. I appreciate.
Okay, do we have any other questions as regards what we've discussed so far? All right. In the absence of any other question, I think we can call it a night here. So by tomorrow, same time, we'll be meeting and then we'll be discussing about three concepts: our AGV, our AGC, our string talk,
Samuel.
our get
How
line.
are we going to do about how are we going to do about the video? How will you share it?
Don't worry, just pay attention to the announcement channel of CodeTrybe group. You would obviously see it
Okay,
from there.
okay,
Yeah.
okay. Thank you.
Please, Samuel, I have just a question.
Okay.
Okay, so it's just like out of curiosity, but I don't know if that kind of thing can exist. So every process or an instance that is created, there is an ID that is being returned. Is there any way or any chance that a process is about to be created? Let's say a parent process wants to create a child process, and for one or no reason, it doesn't create that process or that instance completely because it's supposed to return an ID. So what happens if anything like that doesn't work? Is there any chance like that it could happen? Like a process could not be created and then a value is returned.
Well, your question would be better answered when we are discussing the concept we'll be discussing in 2 days' time, where we'll be using a function called fork, fork, bracket open, bracket closed. Then you understand it more better then. If a process
Okay.
creation fails, if it is successful, from that session you understand
Okay.
this question even more. So let's
Oh,
anticipate towards that class in 2 days' time.
all right. Thank you very much.
Yeah. All right. So thank you everyone for joining in. We'll see you tomorrow,
Thank
same
you
time,
for your knowledge.
7 p.m. GMT. So you should know your time zone.
Thank you.
Thank you.
Thank you. Oh my God, what's happening?
Are you raising hand
Thanks.
to say good night or you want to ask question? Which one?